What are mode shapes in mechanical vibration analysis? Imagine watching a bridge sway gently in the wind or a guitar string vibrate when plucked. These movements are examples of how structures and objects respond when they vibrate. But what exactly determines how they move? That's where mode shapes come into play. Mode shapes are specific patterns of deformation that a structure exhibits when it vibrates at its natural frequencies. Each natural frequency has its own unique way of moving, bending, or twisting. Think of it like different dance moves. Each move has a distinct style and rhythm. When a structure vibrates at a particular natural frequency, it adopts a corresponding mode shape. In vibration analysis, understanding these shapes helps engineers see how a structure will behave under dynamic forces. Instead of just knowing the frequency, they also learn how the structure moves at that frequency. These mode shapes are like blueprints showing which parts move the most and which stay relatively still. This information is essential for designing safer, more reliable structures. Engineers often visualize mode shapes as animations or deformation patterns. These visuals highlight areas with high vibration amplitudes and stress points, helping to identify potential trouble spots. For example, if a bridge's mode shape shows large movements at certain joints, engineers can reinforce those areas to prevent damage. Mathematically, mode shapes are solutions to the system's eigenvalue problem. They are called eigenvectors, and they come from the system's mass and stiffness properties. Each eigenvector corresponds to an eigenvalue, which is the natural frequency. This mathematical approach makes it easier to analyze complex systems with many moving parts. In practical terms, modal analysis uses these mode shapes to predict how structures respond to real-world forces. It helps identify resonance conditions, where vibrations can become dangerously large. Engineers can then modify designs by changing materials, adding stiffeners, or adjusting mounting points to alter the mode shapes and natural frequencies. Knowing the mode shapes also supports active vibration control strategies. By targeting specific modes, engineers can develop systems that reduce unwanted vibrations. Monitoring shifts in mode shapes or frequencies over time can also reveal signs of damage or fatigue in a structure. In essence, mode shapes are a fundamental part of understanding vibrations. They tell us how a structure moves at each natural frequency, guiding engineers in designing safer, more efficient mechanical systems. Whether it's a building, a machine, or a vehicle, grasping these patterns helps keep everything working smoothly and safely.